My name is Noah Geyer, and welcome to my ENME489Y remote sensing project. The purpose of this project is to use a rudimentary LiDAR system to map, 3D plot, and then mesh a scanned target for the purpose of gaining a better understanding of how LiDAR systems work and the emerging field that exists because of them. My particular target is a wooden and black painted metal bench located at the front of Glen Martin Hall. When I initially chose this target, I did not know anything about LiDAR and which aspects of the target would be beneficial or detrimental to my scans. I chose this target particularly because I had run out of other ideas, and as I was walking to class, I passed the bench and decided that it would be at least worth trying to scan. It should also be noted that this particular bench, when I went to scan the object, was located directly under a spotlight, so I shifted my target about 3 feet to the left and scanned a bench that was in a much more secluded area. Additionally, the benches were all bolted to the ground, and therefore they were unable to be moved in order to get better scans of all sides. This is the sensor used in data collection for this class. The chassis is a modified version of the one provided by Dr. Mitchell, separated into 3 parts in order to fit on my print bed. The camera down at the bottom acts as the receiver, collecting the images, and the line laser up at the top acts as the transmitter, making this an active system rather than a passive system that requires ambient light. Everything on here at the moment is secured with this red wire, including the powering for the laser, which is 2 AA batteries taped together. The chassis is designed to hold everything 1 foot apart in order to satisfy the equations in the respective Python codes. The tripod is a custom design because my apartment is very bad with packages, but this resulted in a non-adjustable base and in the end led to some stability issues as well. These images of how the LiDAR functions should be credited to Dr. Mitchell, as they are taken from one of his PowerPoints from lecture in order to better demonstrate the concept. Digging deeper, a traditional LiDAR system operates very much like radar, except instead of sending out a pulse of sound energy, a LiDAR system sends a pulse of laser light energy towards the target. It then uses timing based off of the speed of light in order to gauge how far away the object is, depending on the flight time of the photon. This system is modified slightly in our project, in that rather than using a timing system, we are using an XYZ coordinate system based off an image collected by our camera to determine the XYZ positioning of the object. These XYZ coordinates are generated based off the positioning of the line laser in the image. Theory states that as the distance to the object approaches infinity, the laser will appear in the center of the screen. On the other end, as the image gets closer to the sensor, the laser will appear on the edge of the screen. Using an equation based upon the distance between the camera and the laser, i.e. 1 foot, we are then able to turn these pixel distances into usable XYZ coordinates. This was initially done with a point laser. However, this data was collected before the chassis was built, and therefore is very inaccurate. However, I have included the graphs of the data here for viewing. More accurate calibration was then done with my line laser. Utilizing a large box I had in my room and transferring my TV and keyboard out into the hallway for space, I marked 6-inch intervals on the floor using Scotch tape. These 6-inch intervals were then used to collect line laser data, which was then used to calibrate the laser. These images are included in order to show the difference between close images and far images. These images also show the difficulty in reading the laser. The laser is affected by things such as propagation through medium, the emissivity of the target, as well as just generally ambient light noise. Therefore, the target background, as well as the lighting of the room, has a great bearing on how much data can actually be recorded. In order to turn these images into usable coordinates, we utilized a pseudo computer vision system known as Color Picker. This allowed us to modify the HSV values of a black and white image in order to image only the red laser. This allowed us to focus in on which coordinates we wanted on the image, as well as making sure that those images were only on the object rather than ambient lighting. Computer vision is a method of teaching a computer system to learn how to look for a specific type of information. Color Picker is a computer vision system in that it allows us to determine which ranges of values the computer will gather information from. For example, in this video here, we have taught the computer to look for the center of the green circle on this traffic light. This allows the computer camera to track the image and put this circle around the dot. Moving back to the project itself, collection in the field resulted in a lot of technical and equipment issues. I will leave that up to my past self to describe. Here's the setup. My homemade tripod is currently supported by this chair. The tape is being used to anchor it for whatever angle I need. I have a battery pack that I have borrowed. The phone is taped here typically, and I am scanning my target. Benched, I went at 3 different locations in order to get the whole thing. I am sending my information to my laptop over here. Because the keyboard won't connect, I have a second keyboard in order to operate the programming window and collect the images. I then am going to take those home and run them through MATLAB or Python in order to set up a point cloud of my bench here. So, we'll see how that turns out. These images are one set of data collected on that night. Each image is taken at a specific angle which will then coordinate to a Z position when plotting. Each image was given an exposure time of 20 seconds in order to make sure that the laser showed up in the screen. More than that would result in too much light pollution as well as taking forever. But less than that resulted in poor image quality that couldn't determine where the laser was on the bench. By taking images from multiple angles, we are able to create a meshing of these points in order to create a better picture of the 3D object. Unfortunately, due to scheduling conflicts, I was unable to go out for rescans. Therefore, all of the data points and meshes shown after this are taken from the initial data collection. Python code provided by Dr. Mitchell was then used to turn these images into the set of X, Y, and Z coordinates that would be used to create the point cloud. This code has been slightly modified in order to pull directly from the files divided by each side. That way, the images don't have to be rearranged every time I want to change which side I'm analyzing. As previously stated, an HSV filter was applied in order to determine where the laser was. In order to clean up this dataset, a lot of backspace and delete key holding was used to eliminate all extraneous points as well as those that just simply were wrong. Once these data points were generated, they were transferred over to MATLAB. This MATLAB code is heavily suppressed in order to be able to run quickly for this presentation. However, each mesh was placed into MATLAB and put together using a rotation matrix, which in this case is also suppressed. This allowed the matrix to move the sets of images in order to align them so that they would match the bench shape. Once this 3D point cloud was generated, it was imported into MeshLab. In order to create the mesh, I followed the instructions provided in the homework assignment provided by Dr. Mitchell. However, MeshLab does not run on my laptop. Luckily, I was able to use my father's. However, for the recording of this video, he is not present, and therefore I must use a copy of the image in order to present it here. My apologies. As I leave this text image of all of the technical difficulties experienced during this project, as there was too many to list, I would like to extend a special thanks to Dr. Mitchell for allowing us to learn how to do this, and Ryan Moss for allowing me to use some of his tools to scan. Thank you very much for your time.